Hey everybody, so to kind of coincide with molarity, I'm going to introduce us to titrations. We talked about it last year a little bit at the end of the year. Again, it's something that comes up early in AP chemistry. And titrations are something that are actually pretty frequently used in chemistry. When you go to college, you'll be doing tons and tons of titrations. So, titrations are just a lab experiment that we do in order to figure out a concentration of a certain solution. So usually how titrations are set up is we'll have a ring stand and a ring clamp, and there will be a nice long burette, which is this long glass tube, and it will be filled with a solution, okay? Usually it's an acid or a base, and whatever is in this burette is called the titrant. Okay, again, it could be a acid or it could be a base, and usually we know the concentration of this guy. So usually we could say like, hey, this is 1 molar. I don't know. Let's just say HCl for now. It could be NaOH. It could be HCl. It could be a myriad of different things. But let's just say it's 1 molar HCl. And then down here we'll have a flask with a known volume of some solution. We don't know what the concentration is, but let's just say it's something molar NaOH, and say we have 50 milliliters of it. All right. So with titrations, what we do is we add titrant dropwise. Okay, we add titrant dropwise to this flask, and then all these ions start reacting. Well, what good is that going to do? Well, what I didn't tell you is that in this flask is I put an indicator. Alright? So I put an indicator. And then what happens is that I'll keep adding HCl until the moles of HCl will equal the moles of NaOH. So I'm adding these molecules, and then all of a sudden the molecules all equalize and eat up each other, and they cancel each other out. Well, at that point, what we'll witness here is a color change. Okay? It's different for every type of titration. Sometimes it's from a red to a blue. Sometimes it's from a clear to a pink. Okay? But that is when the moles of titrant equals the moles of, and this guy down here is called our titrate. Okay? So what happens is we keep adding a solution, and then we wait for the color change, and then we'll notice a drop, right? Our solution, we'll keep adding it, and then we'll notice a drop. Well, then we could say, okay, from here to here, this did a color change. The moles are equal to one another, so that means I used, let's say, 10 milliliters of HCl before I got to the color change, all right? Well, now, what can I figure out about this? I have molarity and I have volume. Well, if I have molarity and volume, I can figure out how many moles I used. Okay, so let's do that real quick. Let's figure out how many moles I used. We got 1 molar HCl. I don't know how many moles I've used yet, but I know that I've used 0.01 liters. Okay, remember it's got to be in liters. So I do a little algebra here. I timed by 0.01 liters on both sides, and I realize that I've used 0.01 moles of HCl. Right? Well, the thing about titrations is that when I hit that equivalence point, that color change, okay, I know that, remember, the moles of titrant equals the moles of titrate. So that means my moles of HCl is going to equal the moles of NaOH. Okay, so that means if I have 0.1 moles of HCl, I have 0.1 moles of NaOH as well. And remember, the ultimate goal of this titration was to figure out the concentration of NaOH. Well, I have moles of NaOH. I know my volume of NaOH, my initial volume, which is 0.05 liters. Hey, I could figure out my initial concentration of NaOH, right? Before I added any acid, I could figure out the initial concentration. So I take 0.1 divided by 0.05. I know this in my head, but I'm not confident enough to shout it out. That's what I thought too. So the concentration of this NaOH is 2 molar NaOH. Okay, and that's what we'll be doing with titrations. And right now, I'm going to go to the lab and I'm going to show you how one of these actually work. Guys, so here I have my titration set up. I got my burette here, and I got a known concentration of NaOH, 3 molar to be exact. And then I got this unknown concentration of HCl. That's a question mark, not a 7. It's unknown, okay? So what I'm going to do is I'm going to put the titrate underneath here. I'm going to titrate it with the titrant, and then a color change should occur, and then we could do some calculations here to figure out what's going on. So first things first is I'm going to fill this up with my titrant, my NaOH. I'm going to close the stopcock because if it's open, then the base will fall into our titrate, and we don't want that. So I'm going to go ahead and I'm going to fill this up. Close to the top as I can go. You can't see it right now, but I will go ahead and I will post a picture of what I see in my titrate up top. Now the thing about burettes is that they're different than graduated cylinders. Graduated cylinders, we just read from the bottom up, right? At the very bottom, it reads 20, 30, 40, and increases as we go up. But with burettes, they're a little different, okay? They read the opposite. They start at 0 at the top, and they increase as you go down. So you actually read these guys backwards. So again, I will show you a picture of what our titrate reads, and I'll tell you what our initial reading was. So you just saw the initial reading of our titrant, okay? So let's draw a picture of what's going on real quick. So again, our setup here, we have our burette, which has 3 molar NaOH, okay? Let me go ahead and move this out of your way, the opposite way, okay? And then what we have in the flask here at the bottom is we have 50 milliliters of some unknown concentration of HCl. And that's what we're trying to figure out. Okay, when we initially read this thing, it read something like we'll go with 0.72. So our initial reading was 0.72 milliliters. And now we're going to go ahead and we're going to start titrating this thing. So what happens is that I got this phenolphthalein indicator. It's going to change pink when basic, and it stays clear when acidic. Obviously, I'm just dealing with HCl here, so it should just stay clear. So I go ahead and put it in there, just a couple drops, and swirl it around, and that is good enough for us, okay? So we go ahead and we do that, and then we go ahead and start titrating. We add it drop-wise, and if you can see, there's a little bit of pink that's starting to show up in there. Every time I add some liquid in there, it starts to turn pink. You might be able to see it, a little pink, a little purple. And what happens is I start adding it, and it'll start to change, okay? And you might say, hey, I'm hitting my titration point because it's changed color. Well, let's swirl it around, and it turns clear again. We're not quite there. So we're going ahead, we're adding some more, swirling it. Again, it turns purple. Hey, I might hit my equivalence point. I go ahead and swirl it. Oh, it's getting close. It's getting harder to go away, so it's clear again. So I'm going to start adding it drop-wise because I'm getting real close, and that pink is not going to want to get away. And right now, I'm swirling it, and the pink's staying. Okay, so that means I have hit my equivalence point. So I'm going to go ahead and I'm going to take another picture of our final volume, and then we can figure out how much total volume of our titrant we used. Okay, I read that burette, and it looked like it was somewhere around 20.90 milliliters. Okay, well now we know how much volume of base we used, we know the molarity of base, so now we can go ahead and figure out how many moles of base we used. So let's go ahead and do that. It's 3 molar NaOH. Moles I don't know, but the volume is just final minus initial, which actually I could do that in my head. It's 20.90 minus 0.72, which is, I'll do that up here, 20.90 minus 0.72, which is going to be about 20. I can do this, 1/8 milliliters. Okay, so that's about 0.02018 liters. Okay, we multiply these together to get moles, right? And we should get somewhere around, let's do 3 times 0.02018, and we get 0.06054 moles. And remember, that is of NaOH. But the good thing about this titration is that it's a 1-to-1 ratio of H plus and OH minus. So when we hit our equivalence point, our moles of base will equal our moles of acid, or our moles of titrant will equal our moles of titrate. So that means we have 0.06054 moles of HCl. And remember, we want the concentration of HCl, so we just got to do moles over liters. And we figured out, right, because we hit the equivalence point, that moles of base equals moles of acid. The volume is 0.050 liters. It's a horrible 5, but you get the idea. And we should get a concentration of 1.21 molarity. Okay, so that's what we're doing. We're figuring out how much titrant we used, and then we multiply the volume by the molarity. We'll get a moles of our titrant. Since that's at the equivalent point, moles of titrant equals moles of titrate. Now, since we know moles of titrate and the initial volume of titrate, we could go ahead and we could calculate our molarity. Okay, so that's an example of titrations and how they'll look in the lab. Alright guys, let's do one more titration problem just to help us with the basics, okay? And it says we titrate 25 milliliters of HCl with a titrant of 1.75 molarity NaOH. The initial volume reads 10.5 milliliters, and once we hit the equivalence point, the volume reads 21.30 milliliters. What is the initial concentration of HCl? I should say the initial volume reads 10 point. The initial volume, let's do of the burette. Reads. There we go, a little bit more balanced. Reads 10.50 milliliters. So here, what I like to do is I just like to draw a picture sometimes. I think that helps me out. I like to draw what's in the burette and what's in the flask. Again, NaOH doesn't always have to be in the burette. Sometimes HCl is in the burette, okay? But I know I have 1.75 molar NaOH, right? It's what I'm titrating with. It's my titrant. This is my titrate. And I know I have 25 milliliters of HCl down here. Some unknown concentration of HCl. The burette initially reads 10.5 milliliters, and then after titration it reads 21.3 milliliters. All right? So all we're doing is we're figuring out how many moles of NaOH we used. If we could figure out how many moles of NaOH we used, we could figure out how many moles of HCl we had, because at the equivalence point they equal, and then we could figure out the concentration of HCl. Okay, so here we go. I need to figure out moles of NaOH, I know molarity, and then I just got to figure out that total volume used. So I'm going to go over here, and I know I can take my final volume of 21.3 milliliters and subtract my initial volume of 10.5 milliliters, and I should get something around 10.8 milliliters. So I use 10.8 milliliters of NaOH. Well, let's figure out how many moles that is. Again, my molarity is 1.75. My volume is 0.0108 liters. Let's figure out how many moles that is. So we'll do 0.0108 times 1.75. I have 0.0108 0.189 moles of NaOH. And remember, that is at the equivalence point. So that means that if my moles of my titrate equals my moles of titrant. So my titrant was 0.0189. So that must mean my titrate is also 0.0189 moles. So that means I have 0.0189 moles of HCl. Again, we want the concentration. So moles over liters. My liters was 0.025. So that concentration of that acid was 0.756 molarity. Okay, so once again, we figured out the moles of the titrant. That means it equaled the moles of the titrate. Okay, and then we were able to figure out that concentration because we knew the initial volume was 25 milliliters. Okay, let me throw one more tough one at you, and then we'll move on. Okay, so this next example. Well, let's talk about our previous examples first. So again, that phenolphthalein, that indicator, it changes once the moles of acid equal the moles of base. And what determines that is the H pluses and the OH minuses, right? When these break up, it breaks up into H pluses and breaks up into OH minus and then Na plus, okay? Well, when there's more OH minus, it turns pink. When there's more H plus, it's clear, okay? And when those guys cancel out, it becomes a little more basic. So you actually get a little bit more base. But this is nice because for every one H plus, it will eat up one OH minus because they're both monoprotic. One's got one H plus, one has one OH minus. So it's just a 1-to-1 ratio. But what about if we have something that doesn't just have one hydroxide in it? Now we have a situation where we have something with two hydroxides. So we're going to need twice as much acid in order to neutralize that, okay? So let's do a situation where it's not so simple and we have to have or take into account that we need twice as much acid to neutralize it. All right, guys, so again, we're dealing with a situation where we don't have a 1-to-1 ratio of our H plus and OH minus molecule. Here, we have 50 milliliters of COAH, and we titrate it with 22.3 milliliters of 5 molar NaOH. Oh, not NaOH, sorry. HCl. There we go. What is the initial concentration of our CaOH2? All right, so again, I like to draw a picture. I'll draw it over here. Okay, in this situation, in the burette, the titrant is looks like it's HCl, right? It's 5 molar, and we ended up using 22.3 milliliters of it. And then down here, our titrate ended up being CaOH2. We have no idea the concentration, but we know we used 50 milliliters of it. So we need to know the moles of CaOH, and we need to know the volume of CaOH to determine the concentration. We got the volume, let's figure out the moles, okay? Well, all I could tell you is that I could still figure out moles of HCl, right? I got molarity, I got volume. Let's figure that out first. Let's start with where we know we can start out. I got 5 molar HCl, and in liters, I have 0.0223 of them. My calculator is by the computer. I do 5 times 0.0223, and I get 0.1115 moles of HCl. Now, if this was a 1-to-1 dealio, where it was 1 HCl for every 1 base, then I could just say, hey, moles of acid equal moles of base. But in this situation, we can't, because I need twice as much acid in order to neutralize that base. So what we can always do, we got moles of HCl, we got to get to moles of CaOH2. We can always do our stoichiometry to help us out. Our best friend, seriously, I say that in total legitimacy. It is our best friend for this class. So we got moles of HCl. We do a mole ratio, right, to HCl and CaOH2. For every 2 HCl's, there's 1 CaOH. So I just divide it by 2. And I'm going to need 0.05575 moles of CaOH. Okay, it's just like that. Okay, so now it's not nice that we could just say they're equal to each other. Now we got to do a little stoichiometry, but it wasn't too bad, right? All we have to do now is put moles over liters, right? I'm going to do that over here. We had 0.05575 moles of CaOH. 2. We divide it by our, you know what? I don't like that's crowded over here. Let's go over here by our picture, right? We had 0.05575 moles of CaOH2. We had 50 milliliters, right, to start, so that's 0.05 liters. Okay, we go ahead and we divide that. 0.05575 divided by 0.05, and the initial concentration was 1.115 molarity of CaOH2. Okay, so we had 50 milliliters of CaOH. It was a low concentration. And look how much acid we needed to neutralize it. We had a high concentration of acid, and we had to use a large volume of it in order just to neutralize 50 milliliters of 1.115 molarity CaOH2, okay, which matches with our equation up here, okay? So that's a situation in which you will deal with a non-monoprotic titration, okay? So that is the intro to titration, okay? Be ready for anything where you might have an imbalance and have to use stoichiometry, but also be ready if it's just fine and it's all ones and you don't need to do that, okay? So that is titrations, everybody. Have a great day.